Okay, creature, wild people. I've been working on this for a while. Not that the problem's that hard, because intuitively I kind of knew what to do, but getting it to work out, I was having some issues. But let's just take a look at what they're talking about here, real quick. All right. So, and it's basically the whole idea. The whole idea here is you can break is showing how easily you can break a bone. Now they keep changing this number here, which is the compression, the Young's modulus uh, of what it can withstand. Is the problem I worked before 7.5. This one's 6.4. They haven't changed the Young's modulus for it, so that's good. They keep changing the mass of the bands, and that's fine. And if you added a rotation to it, it would even be much less of a force of a distance would be required. I mean, you don't have to go very far at all. Those of you that have twisted an ankle bad or even broken a foot because you stepped in a hole wrong know that the twisting motion, and that's what athletes fear the most, is getting twisted. They you know that's one of the knocks. That used to be one of the only knocks on why on turf versus astroturf way back in the day in the 70s and 80s. Astroturf was so slick that their feet got knocked out from under them pretty quickly. But but turf, sometimes you get your cleats stuck in there, and that can be a bad situation. But anyway, you're going to see that it's not that far. So, but let's think about what they're saying here. It's and I'll get the things written down as we read through this. So the um, the force is equal to 6.4. The effective force that'll cause it to break is 6.4 times 10 to the fourth newtons. I thought we were supposed to come up with what the effective force was, and not exactly the height that it would fall, because to me the effective force, we can use it as this is a conservation of energy problem, but I was thinking it'd be more like an impact problem. Like what's the, because the actual collision can create a tremendous amount of force if you think about it. But we're allowing for the cushioning of the compression of the leg. So y equals 6.4, and the area is 3.0 times 10 to the fourth negative 4 meters squared, and the length of the leg, L naught, then would be 0.58 meters, and the Young's modulus is equal to 9.4 times 10 to the ninth newtons per meter. Okay, so now, meters squared. So now we've got it all worked out. Let's go look at what I have written down here on the ladybug. We've got that written down. All right. Now then, here's the deal. They're saying you got this MGH before, this MGH at the beginning, plus um, plus you're going to have the Young's modulus at the end, the 1/2 kx final squared, plus because this, it's like we're compressing a spring. Okay, initial squared is equal to MGH final, which we know is going to be 0, plus 1/2 kx naught squared. Okay, well, oh, final squared, which is how far it will have compressed. All right, so already I've screwed it all up, of course. So MGH naught is how far he's going to fall from. This term goes to 0. This term goes to 0, is equal to 1/2 kx final squared. All right, now the key to this is you go, well, if I knew k, I could figure this out without any trouble. Yes, you could. And I knew f, I could figure it out. So the way I have first approached the problem, and it turned out to be, I didn't get quite the right answer. I got close, but I didn't get quite the right answer. I thought it would be this way. I thought I would go, okay, well, look, it's going to compress. you know, how much energy do I need to get the spring to compress a certain do I have to go from to get the spring to compress? And I thought, okay, well, I've got F over A is equal to Y times delta L over L naught. That's what I was thinking. And my thinking was right, but I think I plugged something in wrong to the calculator. And then I solved for delta L and stuck that into here, but I didn't know what K was. K was kind of tricky. And so, yeah, but then I got to thinking about, well, what would K be? Well, if we look at this thing, look at this. We've got the force. Let's look at, now this is how they do this. The force that it's going to fall is equal to Y times A over delta L times L naught, or delta L over L naught. Okay, well, we know this with a spring type, with a spring, Hooke's law. I'm going to invoke Hooke's law here. Dun dun dun. Here's where we get here's the big idea, is YA over L naught is equal to delta L, which is the same thing as KX. Yay! Where K is equal to YA over L naught. And delta L is equal to the X. So here's my K, and this is equal to the X. All right. So I was on the right track. But it didn't work quite out. So I'm going to show you how to finish this problem. But here's the big idea, and then the rest is just plugging and chugging with crazy algebra.